Now we're going to start talking about types, data types that is, operators, and expressions in the C language. Data types actually limit the contents of an item. So that we have a variable, and let's say that it's a character, that's the char or char, or character. It could be an integer, a floating point, or a double precision floating point. A double is just a larger float with greater precision. And of course, we'll look at all of these in details as we go through this section. You can also have shorts, longs, signed, and unsigned. And shorts and longs relate to integers, and that says how many bits there are in the integer and what's the largest and smallest, most negative number that you can have held within that variable value. And of course, an unsigned cannot go negative. It can be 0 or a positive value. And a signed, which is the default, if you just make an integer, it will be signed, so it could go negative. A character the same way. You can have a negative character, and we will look at those maximum, minimum, maximum values as we go through this. Operators are used to test and change the values of variables. We have the multiplication, division, addition, subtraction. Across here are standard arithmetic operators, and then we get into comparisons: less than, greater than, less than or equal. These two together make that up. Greater than or equal, this is a separate operator. That's a single operator, even though it's two characters, just like that one. This is an equality, is one thing equal to another thing. We'll see that later on. And you do not use less than, greater than for not equals. We use something with the exclamation point and an equal sign. That's not equals there, the operator for not equals. So we'll see all these in great detail as we go. And then a C expression is a combination of variables or data types and operators. And we can also have constants. We haven't talked about those yet, but we will. And a constant, of course, is something that you set a value to when you create it or initialize it, and you do not then change the value. You're not allowed to change the value of a constant, or it wouldn't be a constant. So an expression is made up of, here we have a variable called a, and it has an assignment operator of equals. But notice that's different than an equality. Is one thing equal to another is very different than this thing is equal to this thing. That's the left side, or what we call the L value. You'll see that is set equal to the result of this variable, or it could be a constant. We don't know yet at this point. Added to this variable or constant. Of course, we have our semicolon that makes the end of a statement. So that's the section that we're taking a look at now, types, operators, and expressions. So hang on and go on to the next section here, and we'll dig into this in some detail. Now we're going to talk about variable names and some of the restrictions that the C standard puts on variable names, so that we know what the rules are when we make up a name of a variable to use in our program. You make these variables, as you probably figure out. I'm sure you have a little bit of knowledge of programming by this time. We make these variables so that we can store things in them, like a name or an address or a zip code or a billing amount or something like that. So when you make a variable name, you of course want to try to make it so that it reminds you of what's in there, of what you're using the thing for. Some of the restrictions, though, we see that our first character must be a letter. Variable names in the C programming language are case sensitive. The standard calls for the first 63 characters to be significant and the first 31 for external names, for example, function names. Let's take a look at some details of this. Variable names starting with an alpha. There you can see that the character array that we have, which is going to be a bunch of characters put together, we haven't said how big yet because there's nothing inside those little square brackets. You'll see how we do that, of course, when we get to arrays and those kinds of things. But we care about the first name right now, talking about variable names. So there we have a character first name. That's just fine. It starts with an alpha. You understand what it's for? Good. character first name with a 1 though. Can't do that. The compiler will complain about that, and it will error out on you because you cannot start a variable with a number. The first name there we see on the third line with an underscore in it, that's just fine too. It's quite all right to put underscores in the name in the middle of your variable names, and it helps you kind of break things up if you have to put several different words together to properly describe the variable name. That one on the bottom is legal, but you really shouldn't do it. You definitely cannot use, you do not want to use, I should say, 2 underscores at the beginning of a variable. The C++ language defines that. So when you go over to C++, you don't want to be in that habit of having 2 underscores in the front of there. And you don't want to use a single underscore in regular C either, because many times the compiler will use a variable with an underscore as the first character itself. So we don't want to do that so that we don't accidentally get crossed up in what the compiler is trying to do when it compiles our code. So really, it's just easier if you don't. Just don't use an underscore as the first character of your variable name. Variables names are case sensitive. So there you can see first underscore name, first name, and character first name all in lowercase. Those are all different identifiers. And that would be very confusing inside your program when you're referring to those different first names with an underscore or without an underscore or without any uppercase characters at all. Those are all different to the language, and they would all be different locations in memory, and that would be a problem. Just for us trying to figure out what's going on in the program. By tradition, we use all uppercase or all caps for constants. There you see a constant getting created. As we look at the preprocessor, we'll talk more about pound include, and here you see pound define. Here we're defining the letters P and I, or pi, as the value 3.14159, and you can extend that out a bit if you like. But we use that all caps because then when you're looking through the program and you see an item that is in all uppercase, you can figure that that's a constant, and you don't accidentally try to set it to some other value or try to do something with it that would be illegal for a constant. That's our tradition for naming constants. When you're creating a variable name, the first 63 characters of the name are significant. By the standards and the rules, if you had a 64, 65, whatever character variable name, you're not guaranteed for that to be unique, and the compiler is allowed to complain about it. In reality, though, today's compilers, for example, our Microsoft C compiler that we're using, it will go out 2,048 significant characters. If you have a variable name that is 2,048 characters, you need to start your programming career over again because there are other issues involved. So as far as the standard is concerned, 63 characters count, but there's really many more. When you're creating a function name, because functions can be in different files and they can be brought together by the linker, only 31 characters are guaranteed for an external name, a function name, or the name of a variable that is available to other pieces of code outside our file. Because remember that a C program can be made up of a bunch of different C source files, and all of them are compiled into object code, and then all of that object code is linked. So when one piece of object code refers to a function that's in a different piece of object code, it calls it by name. And those names are only guaranteed to be 31 valid characters long. Again, in practice today, you'll find that most linkers will go way beyond 31 characters, farther than you'd ever have to care. Should you ever get into a programming environment, though, creating embedded code, the kind of code that would go inside a calculator or some piece of machinery or a car or something like that, that operates a piece of machinery, that's called embedded programming. Sometimes those function names will be smaller because they're dealing with limited amounts of room, limited space in the tiny computer that they're working with that's embedded in some appliance or a small palm top product, something like that. So there we see that we have some limitations by the standard, but in all reality, it doesn't really come through as being much of a limitation for us anymore. All right, let's go on to the next section. We're going to talk now about C language data types and sizes of those data types. C doesn't have really that many data types. They're pretty simple. There's a character, which generally is 1 byte long, and it is designed to contain one printable character. There's an integer, which usually is 2 bytes long, and that holds one whole number with no remainder. A floating point, or a float, is generally 4 bytes of storage and will contain one floating point number. A double takes 8 bytes of storage, but it still only holds one floating point number. That number just has much greater precision. You can be much more precise. That's usually used for higher math, graphics, computational things like that, not dollars and cents or anything along that line. There's also modifiers of short and long, which will change the number of bytes used for storage and the minimum and maximum values. But the short and long work on the integer and makes a short int and a long int, and then there is such a thing as a long double as well. Here's a little chart to give you an idea in the Microsoft C compiler and its implementation on traditional non-64-bit architecture of what we have for storage. So there's a character, a char, 8 bits long, and since it is signed by default in the Microsoft compiler, and that is dependent on your machine, whether that standard character will be signed or unsigned. In our case, it is signed. It will go from a maximum negative value of negative 128 up to 127. An unsigned character, of course, cannot be negative. It still takes 8 bits of storage, and it goes from 0 to 255, all 8 bits set on. An integer is 32 bits, and there you see the negative and large negative number and large positive number. I'm not going to bother to try to read that number off to you. We only have so much time. There's an unsigned integer of 32 bits, and of course being unsigned, no negatives, 0 to 4 billion and change. There's the short for 16 bits and the unsigned short for 16 bits, and you can see their values, minimum, maximum. Longs are 32 bits, and remember that is a long int, so it can't hold anything but a whole number, and an unsigned long. And then we have our floating points and our doubles, which gives you an idea of just how large a number can be stored in each of those, in floats and doubles. So that's all there is to it. C does not have a lot of tough types to have to deal with, but you have these basic types, which you can then build into all sorts of other kinds of storage options, other kinds of variables that will be usually more than sufficient for what you need to do. Remember, some of the greatest operating systems were written with this language. So it is simple, it is low level, but it is quite powerful. So we're going to move on and take a look at some other kinds of variables and constants and a lot of other things as we continue with our types, operators, and expressions. Now we're going to talk about constants rather than variables, which we've been discussing so far. Constants are just that, constant. It's an unchanging value. The compiler can do special things with constants and use them throughout the compile process without consuming the storage areas that the compiler would use for variables, because the compiler would need to keep those in special places in memory so that true values can be put into the variables and recovered, manipulated, so on, changing strings or adding values to numbers, that sort of thing. But a constant, we don't expect it to change, so the compiler doesn't have to take up space for it. Constants can be specified when you create them in decimal. There you see the decimal 123 that we know at 123. It's inside single quotes. That shows that That's a decimal value which will be defined into a constant. Octal simply has a leading zero, like 0173 is also 123 decimal. And hexadecimal, 0x7 Baker, or 7B, is again 123 in decimal, the value that we know. So that's some ways that you can specify constants and use different notations. Maybe those notations would make more sense to you in your application. Constants are created with pound define. There you can see 4 lines of code. Notice the pound define for PI, 3.14159, and an F for floating point right there. That will cause pi to be created as a floating point value and not just an integer. This one down here, max records, we've pound defined max records as 10,000. That will be an int. It's up to your compiler whether it makes it an unsigned int or not, but this will be an int. Max days of the month, 31, that is also an int. And then we defined at the bottom U.S. Census as 300 million. Now there we have to put an L on the end of that, and that will specify that as a long. So U.S. Census as a constant will be a long and will be used in mathematical functions as a long. So there, when we see casting later on, how values are cast to one type or another, depending on the math functions being performed on them, U.S. Census will already be defined as a long and make the math function that much simpler and the code that much faster. Here's a bunch of escape sequences that are generally used in constants or sometimes in string constants. You've already used one of them. Notice the backslant A, that's for alert, and there's backspace and form feed and all sorts of other things. You've already used the backslant N for new line. An R is a carriage return, there's a tab, and then you can use some special things like the backslant and 3 digits of an octal number or backslant X and a hexadecimal number to create sequences of special codes in your constants that you create. If you want to actually show a backslant or a single or a double quote inside a string constant, you have to escape it out like this with a backslant in front of it so that it doesn't get picked up as another backslash or as the ending double quote of a string. Remember, hello world started with double quotes and ended with double quotes? Well, if we wanted to put a single quote or a double quote inside the string itself, we would have to escape it with a backslant in front of it. There is a special constant, backslant 0, which is null, all zeros. So it also can be used mathematically, but we mostly use it at the end of strings and to show that the string is over. We don't use a length byte in front of the string like some languages or some implementations do. C programming relies on that null, and you can check for things to be null by comparing them to that quote backslant 0 quote that you see, which is null. String constants we've already seen, for example, hello world that we used in our first program. So hello world backslant N is a string constant. And when it's stored in memory, it's really an array of characters. We have HELLO space and world and the new line character, and then we have the double quotes to end the string. But in memory, we have hello world and a new line byte, and then there's really a null out here on the end. There's one of these backslant zeros or an end of string character, so that when C runs through memory and looks at this sequence of characters, there will be hello world, the new line, and then the null, so it knows where the string stops. So when you're defining constants, single quote A single quote is a integer value for the letter A, and that will be coded as the value of a constant. But that's very different from double quotes, A double quotes. That's the letter A, or the numerical value for it, and then there's a null next to it. So there's really 2 characters taken up there, because this is a string constant as opposed to this being a character constant. There's one more kind of constant, and that's the enumeration constant. And it's a little bit special. It's called enum. And there we have an enum, short for enumeration. Boolean is the name of the constant. And we have an opening brace and a closing brace. So we have no is 0 because the first value inside the braces will be given the value 0, comma, and then the next value will be given 1, and so on out the list. Then we have a closed brace and semicolon to end the statement, the enum Boolean statement. Down here, we're going to make up an enumeration constant called months. And months can contain the value 1, 2, 3, 4, 5. As you see, we run down the line here. Notice we said Jan equals 1, January equals 1, because we, of course, didn't want it to start out by default and set January equal to 0. We need it equal to 1. So we can force that on the enumeration anywhere in the list, and the enumeration will just increment the number and run us all the way out to 12 out here. And we'll see later in some of our programs how you actually use something like this. But it's a good way of getting values into your code that are easily set up, and you don't have a bunch of pound defines and things like that kind of cluttering up your code. So enum is a nice thing to be able to use. And we're going to move onward to other types, operators, and expressions. We're going to take a few minutes now to talk about declarations in the C programming language. A declaration of a variable is very different from the initialization of a variable. The declaration tells the C compiler that we want a certain number of bytes and a certain type of storage for some use that we have in our program, that we want something that we can put a name or an age or some other piece of information in. So we're going to declare variables in here. Now, declaring the variables all on one line is just fine. Here we have some integers. We have an int called upper and lower and step. Now, this creates those variables, but it doesn't give them any initial value. We'll take a look at a point here where they would get an initial value based on where they're created. But if they're just put in our normal program, they are what is called automatics, and they will not be given a value. Just whatever is in the computer's memory where they're assigned to is what you get until you initialize them. It is better coding practice in C to use separate lines, to have character, first name, this is an array that we'll see a little later with the brackets. So we have a number of characters put together there. We haven't said how many yet, but we're just getting set to be able to do that. And here's a character last name, another array. Here's an integer age. Again, no initialization, just declaration of the variable. Now here's an option where we have created an external variable. Here's an integer I, and it's outside of our program. Here's our little main program, or our main function, which at this point is our entire program. So this is an external variable, and it lives in a different place in the computer than this integer I does down here. This is an automatic, and it is declared and initialized at the same time. So here we declare an integer I, and we set it equal to the value 0. So that's our best practice, is to get that thing set to some known value before we ever try to use it. This integer I, because of the way C programming works, will be set to 0 as well, because externals are automatically initialized. They are given a 0 value if you don't give them any other value. So that's a little difference in our C programming declarations. So that's about it for declarations. They're very simple to do. Very simple to create a number of variables. And again, you do want to do them on separate lines, because if you have to come back and maintain this program, you want to be able to just add an extra integer or another variable right at the end, rather than trying to figure out where to put the thing on a single line like we had in that earlier slide. Declarations, very simple, and now we'll be moving right along. Let's talk about the arithmetic operators in the C language. Pretty simple. They are called binary operators because they take two operands. You have one thing added to another, one thing subtracted from another, division, multiplication, so on. There are also unary operators that we'll see later on that operate on just a single operand and make some modification to it. But these are the binary operators. They're very standard from grade school: addition, subtraction, multiplication, division, and we have a new one called the modulus or modulo, and that gives the remainder. We'll take a little closer look at it in just a second. Very simple: x equals a plus b. We use parentheses to change the order of calculation. Here a and b would be added together and then multiplied by c. As you know, if you left the parentheses off, multiplication has a higher order of precedence, so b would be multiplied by times c, and then a would be added to it if you didn't have the parens. So we use the parens, typical math, and as I said, the multiplication and division are performed before the addition and subtraction, and everything associates left to right across the program. Now here's the modulus, or percent sign. It's the character that we use for that. Modulus returns the remainder of integer division. So let's say that we have an integer a has the value 5, and an integer b has the value of 2. Well, if you do a modulo b, that will return the value 1, which is the remainder. 2 will go into 5 twice, and with 1 left over. So that's what the modulo gives you. Just simple, if we said x equals a divided by b, that would give us the 2 times that b fits into a, that 2 fits into 5, but the remainder would be lost. So we need the modulo to be able to use that. Since floats and doubles return their precision values, there isn't any issue with the whole number or the remainder. The modulo is unnecessary and will throw an error. It doesn't work on floats or doubles. So that's all the binary arithmetic operators. Simple, straightforward. Let's move on. Well, now we want to talk about some operators, some relational and logical operators. These are the keys to us getting anything done in the language so that we can compare results that are produced by all those arithmetic operators that we just looked at. So relational and logical operators. We will look at relational, equality operators, logical operators, and then the special one, the unary negation at the end here. Here's an example of the less than relational operator. We have our little program, and we'll use this simple program for all of these operators because it is simple and it's pretty basic concepts, but I just want you to see how they're used in the program. Here our little program says that x is equal to 1. We define x with our definition, and we do an initialization or an assignment all at once. We put 1 into x. So see, we're doing everything in one line there. Now we say if x is less than 5, just for a piece of work to do, we will print that x is less than 5 in a new line. So that's our relational operator, less than. Here's a greater than, same program. If x is greater than 5, x is greater than 5. If, of course, this is not true, the execution would continue on, and in this case it's going to hit our closing brace of main and quit. And that was the same thing in our previous program, of course. So we just have a little one-liner here in the if x is greater than 5. We can combine operators. This one is a greater than or equal to relational operator. If x is greater than or equal to 5, printf x is greater than or equal to 5. Now I threw a little extra in here that we'll see later on, but not in a whole lot of detail. It's just a nice little piece that is good to know about in the preprocessor. This backslant right here, this is a line continuation character. So x is greater than, we can slice that right there and continue the sentence, the quoted string here, on the next line. So the preprocessor will pick this up and it will see that character early on before the compiler ever gets a hold of this. And it will put this whole sentence back together the way it should be. So you want to make sure, since we don't have a space there, that you do leave a space here at the beginning of the line so that the preprocessor gets your spacing right. You want to try to avoid this if you can, but if you do need to wrap a line like we need to here because we don't have a lot of screen real estate, it's okay to use that backslant and come down here and still get your double quotes. Okay, just wanted to throw that one in there for you. So that's our greater than or equal to relational. Here's a less than or equal to relational. The comparison and then the equality. The comparison always comes first. There is no such operator as equal to less than or equal to greater than. You can't switch these two around, just so you know that. It has to be this way with the less than or greater than before the equal sign. So if x is less than or equal to 5, we would do the printout, the printf as before. Here's an equality operator. Now we're looking for the comparison. Are they equal? This is very different. Notice these two. This will drive you nuts sometimes if you mess this up. If you accidentally put a single equal sign in here, if x is equal to 1, that will always be true because you are saying, just like you did up here, x equals 1. And the compiler makes the assignment. X is now equal to 1. You then compare the value of x to see if it's true. It is 1. It is true. And this will drop right on into here. No matter if you said if x single equals 27 or something else here, this printf will still go off because a single equals of an assignment is always true. So be very careful about single equals and double equals when you want to do a comparison or show equality. So here we're saying if x is equivalent to number 1, printf x is equal to 1 and a new line. All right, just be aware of that. Single equals for assignment, double equals for equality or comparison. Very important, very time consuming if you forget that. Here's not equal. If x is not equal to 1, we'll print that out. We use an exclamation point and an equal sign to show inequality. Now these are logical operators. This one is a logical operator and. We say here x is assigned the value of 2, y is assigned 3. If x is equal to 1 and y is equal to 3, then we'll print this out. Now here's an important part about C. C will evaluate this statement left to right across here. So C will do this test first, if x is equal to 1. Now it is not, because we assigned it the value 2. So this test will fail right off the bat. C understands that you're using an and, 2 ampersands together, and that both of these have to be true for the whole statement to be true. So since this has already failed, this statement will quit early and will drop right down here, and we will never evaluate this right side over here. So you're going to see later how you can modify things while you evaluate them. If you try to modify something while you're evaluating over here, this modification will never get done. Like if you try to increment y, or you try to add a value to it, or who knows what you want to try to do over here. Just be aware that using this logical operator like this and, you won't get there if the left side of the logical operation is false. Here's an or. If x is equal to 2 or y is equal to 3, then we would print this out. X is equal to 2 or y is equal to 3. Now, in this case, we don't have that problem with the left side being evaluated first and then the right side, because C understands that with an or, it needs to check both sides. So it will look to see, is x equal to 2? And whether it is or not, we know because this is an or, we still need to look over here and see if this side is in fact true or valid. And if they are both true, then we will get our printf down here, x is 2 or y is 3. Either one. If either one, I want to make sure I said that right. If either one of these is true, this is an or, this or that is true, then we will satisfy the test and we will come down here. X is 2 or y is 3. Now here we saw this unary negation, or half of it earlier. We saw an exclamation point and an equal sign for not equals. Well, this is a not by itself. The unary negation. We call it unary because it works on a single operand. It doesn't need two things to compare. So it's unary negation. Here we say if this result, and what we're doing is we're trying to see if that variable result is non-zero. If it is non-zero, we consider it to be true. If it is zero, a null value or zero value, then it is not true and the if will fail and we will not go in and execute the statement after the if. So we say if result, we would print out result is non-zero if this is in fact the case. Down here, if not result, this printf will happen if the result is equal to 0, because the not reverses whether it's 0 or non-zero. So we would print out that the result is in fact 0 by doing a not result. If result had the value 0 and we do a not result, the not or the negation makes this 1. If result is anything but 0, the not leaves it alone, and we don't wind up down in here. We have not result. We would only get here if result were 0 in the beginning. So now we're going to move on to some other things, type conversions and all kinds of other interesting language issues. And I will even have some tasks for you at the end, a little bit of homework for you to do when we get to the end of this chapter. So hang in there. Let's take a minute and talk about type conversions. We've talked about a lot of the different types that are available: characters, ints, shorts, longs, floats, doubles. But if you're going to perform arithmetic operations on those different types, the types have to be the same. You can't multiply a character times an integer or an integer times a float or divide the two or do things like that of separate or differing types. So what happens is something called type conversion. The operands on either side of an operation need to be of the same type for the math to be performed properly. Then the result, as it is assigned into the left side of the equation, the other side of the equals, it needs to be typed properly so that it fits into the resulting area. Generally speaking, smaller types, characters, will be promoted to ints. Ints would be promoted to longs, and so on up the food chain until you get up to doubles. Sign conversions, if you have unsigned values getting promoted or demoted into a signed value, characters to integers, and so on, the sign conversions are handled by the machine's implementation. Some machines use a high order bit for signed, some don't. Our Intel machines do, that we're talking about here. If it's Linux on Intel or Windows on Intel, they use the high order bit to show sign. But different promotions and demotions are sometimes performed by stripping off the high order bits, as many as necessary to demote a value down into a lesser type. And sometimes high order bits are extended, and whatever is in the high order bit is extended across a number of bytes to promote a value, and that can cause a little bit different outcome than you may want. So it's something to be aware of in your programming. Here's the general rules, and this is straight from K&R. If either operand on either side of the operator is a long double, then the other one will be converted to long double. If either is a simple double without the long extension, then convert the other to double. If either is float, convert the other one to float. Converting then characters and shorts will be promoted to integers if one is an int and the other is not. If either operand is a long, then you need to convert the other to a long to do the math properly. So that's a simple rule of thumb there. And again, you can find that in K&R. Now there's another way that you can do a type conversion, and that's forcing it yourself with a cast. Sometimes that helps you to be able to read the code more clearly, and it certainly helps the compiler because you can expressly say in your code exactly how you want something converted. So here, regardless of what X might be, it could be an integer or a character or who knows what up here in our program, we are going to pass it into the square root function. Well, now square root wants to have a double coming in. And what we are doing here is inside these parens, we use the word double, and that is a cast. That is a type cast. So we are casting x to be a double before it ever goes into the square root. Now, x itself is still up here in memory. It is not changed because what we are really doing is passing the value of x, whatever it happens to be at the moment, into this function. And in this case, we're saying that the value of x will be cast to be a double, the appropriate number of bytes and floating point and all of that before it goes into the square root function. Square root is defined in the math.h library to return a double, so that's what will come out of square root, and it will go into y. Now, if y is not a double, the result will be demoted into whatever y happens to be. So if y is a character or something like that, we're going to lose information because we're going to take the square root of x, and it's going to probably not be a whole value. Of course it could be, but if it's not, and it gets stuffed into a small type over here, then we could lose information. We need to be aware of that in type conversions, that it is entirely possible to lose bits off of, in our case, the leftmost end of the byte, and you wind up with a different value than you thought you were going to have. So that's typecast and type conversions, and we'll keep on going with some more C programming. Let's take a few minutes and talk about the increment and decrement operators in the C programming language. Increment and decrement do exactly that. They add one or take away one from the value of a variable, but they're there so that you can tell the compiler that that's exactly what you want to do. Now, most optimizing compilers now will figure out when you create a construct of adding one to the value of a variable, they will figure out that's what you're doing, and they'll create the best code that they can. But it never hurts to tell the compiler exactly what you want, and that's what increment and decrement do for you. There's a pre-increment and pre-decrement, and there's a post-increment and post-decrement as well. And we're going to take a look here in a second at what that means and how to be careful about how to use those. Now here's a regular increment. It's done in both what is called postfix and prefix notation. So here you see we set up x equal to 1, and then we come down here to our if. If x plus plus is equal to 1, then we'll printf x is now 2. What happens here is that we look at x and compare it to 1 before we do the increment. So you see x is here, and then the plus plus is to the right. That's a postfix increment. So we do the comparison, then we do the increment. So when we get down here, at this point, x would now be equal to 2 because we would have incremented it after our test. This is the prefix notation. Here we increment x ahead of time, and we say if plus plus x is equal to 3, it used to be 2. If it's now equal to 3, we'll print out x is now 3. Since we have a prefix increment plus plus x, x is in fact now 3 before the test. We do the increment, then we do the comparison for equality with this value on the right side. So x is in fact now 3 after we come out of this. Decrement works just the same way. Here we're going to set up and say that x is equal to 2, and if x minus minus decrement is equal to 2, that's our postfix, and that will be the case because we will do the comparison first because we have the postfix decrement. We'll do our comparison. X is in fact 2. We'll come down here and we'll say that x is now equal to 1. Because we have decremented x at that point, so it has gone down to 1. If we now do a prefix decrement, minus minus x equals 0, we decrement first, x is 1, we decrement it again before the comparison. Now it is in fact 0. This will be true, and we will say that x is now 0. So that's the increment and decrement, postfix, and prefix. So now we're going to move onward with some other types, operators, and expressions. Let's take a look at some of the bitwise operators that are available to us in the C programming language. These are going to work on the bit levels of the values of our variables. So since we are working at the bit level, we cannot deal with floating points because floats are stored in a totally different format, in IEEE floating point format. They're not considered bitwise when they're in the variable, so no floats. Integrals only, or integers, characters, ints, shorts, longs, no floats or doubles from this point out. We have AND, OR, XOR, left shift, right shift, and one's complement. Do not worry if you don't get these. If you don't understand these, or you don't have to understand them right now, you may not ever even use them in your C programming career. These are mostly used by people that are programming in C in an embedded format, is what they call it. They're writing programs that are going to be inside appliances or cars, or most likely some piece of machinery that they need to be able to check on the values of registers to see if a motor is turning or running, or if there's a certain temperature being set. And they will set and look at these bits and change the bits and move binary values around inside these variables. So that's why these things are in the language, but they're at this point in K&R, and I just want to show them to you, give you an idea of what they are, how they're used. We won't even go into why they're used, like exclusive ORs and things like that. You can get into some pretty intense logic discussions there, and that's not what we're here for. So let's take a quick look through the bitwise operators. Here's a single ampersand, which is an AND. Remember that we had a logical operator of AND that was two ampersands together. This is just one. This is a bitwise AND. And what this will do is mask bits. It will take bits out of consideration. So there, let's say we have X has a value of 193. This is 193 in binary. So this means that these bits are set 128 and 64, and a 1 down here gives us a value 193 in binary. We're going to have a new variable called Y is going to be set to X, ANDed with a hexadecimal value F0, FOX0. This is the value F0, a 1 in all of these high order nibble positions and 0 in the low order nibble down here. So this is F0, and we don't care what the decimal value is, the numeric value. We care what the hexadecimal value is with all these bits turned on, because that's our mask. So if we mask this together, if we AND this together, the only bits that will come through are the ones that are in this byte, because in this part of the byte, we say if this bit and this bit are both set in the mask, then the bit down here should be set in the result. These bits are not set in the original value, but they are in the mask, but it still doesn't work out to be an AND, so we get zeros down here. And down here, we're not masking these. We don't want to see those down there, so this one does not come through. So we only get whatever bits were set in the high order nibble of our byte of 193. So here we have ANDed with F0, and our result will be 192, which is 128 and 64. That's these two high order bits right here. So that's a bitwise AND. This is called an inclusive OR, and this is used to turn bits on in a value. Again, we start with our 193, 11000001, and we say that Y is equal to X ORed with our F0. There's our F0 again, and our result is 241, because what we say is if this bit or this bit is turned on, then the result should be turned on. If this bit or this bit, then it should be on. This one or this one, it'll be on. this one or this one turns on. This bit or this bit are not turned on, so we get a 0. This one or this one, nope. Nope. This one or this one, yes. That one's on, so that brings that bit down, and our new value is 241. So that allows us, when we OR things, to make sure that bits are turned on. And if bits are already on, that's okay. They'll still pass through. But the OR will make sure that we get these two turned on as it comes through. This is the exclusive OR operator from our bitwise operators set, and it's the caret, the up arrow there. And exclusive OR means one or the other, but not both. So here if we have our 193, that's the binary value for that. Y is equal to X, exclusive ORed, or XORed they call it, with F0, that's our pattern. All ones there, zeros there. Y will be equal to 62, because we will look at these bits, character by character, bit by bit, and an exclusive OR checks this bit and this bit. Is this bit set or this bit set, but not both? Well, here we have both set, so that means it does not make it through. It's false. Here they're both set, and that does not come through. Here, that one's not set, but that one is. So that does match one or the other, but not both. So we will get a true value out of that. Same thing here. This comes through. Now here is one or the other set. No, they're not. So that's false, false, false. And this one, yes, that one is set. That one is not. That matches our exclusive OR and does make it through. So our new value after being exclusive ORed with F0 is 62. That's the exclusive OR operator. Here's our bitwise operator's left shift. And what this does is cause our value to be shifted to the left as far as the bits go. In the binary format, shifted a number of bits to the left. So here we have our X is 193. There's our value. And our new value will be equal to X left shifted by 2 bits. So we're going to take the whole thing and run it to the left 2 bits. So this 1 winds up here because it's shifted over by 2. And the 2 ones that were right here roll off into space. They disappear. These bits are padded in with zeros at the end. New bits coming in either way will be zeros. So our new value is 4. And they use this sometimes to move bits around from a register from one place to another, but you probably won't have a great use for it right away. But that's a bitwise left shift. We also have a bitwise right shift. And the right shift, again, we start with our 193 right here. And now Y is equal to X right shifted by 2. And this causes these 2 ones to shift down to here because they're right shifting by 2. And then our 1 that's here falls off into space and goes away. So we're left with zeros there. The new bits that came in are also 0. So we get a new value of 48. And that's a bitwise right shift. The tilde, or this little squiggly here, it's a tilde, is called the ones complement. And ones complement will flip all the bits. Whatever the value they are when you start out, they'll be reversed when you're finished up. And this is called a unary operator because it only has one operand. Before we had 2 things. We had one value operated on by another value. Ones complement's a unary operand, so we only have the one operator character here working on a single operand. Y is equal to the ones complement of X. X is 193. There's our bit pattern. And here is Y equal to 62 at the end because the ones complement of X is all bits flipped. 0011 instead of 1100. And here 0001 turns into 1110. And so that is our result. The ones complement of 193 is 62, flipping all the bits. Well, that's all of our bitwise operators that we need to really concern ourselves with. So let's move on to some other types, operators, and expressions. Let's take a couple of minutes here and talk about what's known as an assignment operator. The assignment operator is basically shorthand. It performs an arithmetic operation and an assignment into a result location, a result variable, at the same time. These are great because they're easier to read and they are easier on the compiler. The compiler can take an assignment operator and make a better decision about the code, just like with our increment and decrement operator, the plus plus and minus minus. The compiler can, like I said, make a better decision on the kind of object code to create to perform the job because we have more accurately described the job that we're trying to perform. The assignment operators are available to all binary operators. Now remember, a binary operator is one that has two operands. It has one on either side of the operator, on the left and the right. Then the result of the operation is put to the left side of the equal sign into a result variable. A unary operator, as we remember, is one that only has a single operand. There's not two of them together. So there you see we have times or multiplication and assignment. Here's a division with assignment. These are two characters together, but when they are put together like this, the compiler sees them and the compiler understands that this is an assignment operator. Here is a plus equals. That's the one you'll see the most often. Plus equals, a subtraction, minus equals. Here's our modulus. Still works the same way, but performs the assignment at the same time. This is our bit shift left. We saw just in our previous talk, bit shift right. And here's a bitwise and exclusive or and or, all with assignment characters as well. So here you can see x plus equals 5. Now we could have written this out and might have in an earlier language x equals x plus 5, but that's just the long form. This is what we say now in C, x plus equals 5. It means exactly the same thing and exactly the same result will occur. 5 will be added to the existing value in x, but it can be faster because the compiler doesn't have to figure out that it needs to go get this variable value, add 5 to it, take the entire result, and store it into x. It understands that you want to take what is in x, add 5, and put it right back again. Plus, once you get used to the language, this x plus equals 5 is a little more intuitive. And when you start to write longer statements with many more permutations in here, many more operators and other formulas and things like that, this is just a lot easier to code. It's a lot easier to debug for your maintenance programmers. And if you are a maintenance programmer, this thing will be easier for you over time to look at and understand what the original programmer's intent was with the assignment operator. So it's just the right way to do things, and we will be seeing it in our other code as we go on through. But I want you to make sure to get a good grip on the assignment operator at this point. I want us to take a look at something now called a conditional expression. The conditional expression can look very strange, but it's really kind of simple. And once again, it helps us be very clear about what we need to accomplish so that the compiler can create the best code possible. Now here's the format of a conditional expression. You have a test over here. This is the first expression. And this can be an assignment, a test, any number of things that make up a C expression that we've already talked about. Then you have a question mark. This is one of the characters of the conditional expression. The conditional expression is made up of a question mark and this colon over here. So here we have this evaluation that we do. If this evaluation comes out to be true or non-zero, remember true is non-zero, a zero result from this expression, no matter what this thing actually is. It could even be a function call. If the function call returns 0, then this would be false. This would be a false expression. If this expression is non-zero or true, then whatever is in this expression in between the question mark and the colon will be performed. It can be another function call, a number of statements, whatever. It's another C expression inside here. I put a little T there to show you that this is the true expression here. If this expression resolves to be 0 or false, then this series of statements, this expression on the right-hand side of the colon is what gets executed. So here's an example down here. Here's our assignment that we're going to do. So this is not really part of the conditional expression, vote equals. That's just an assignment when we're done. Here's our little test. This is this part right here, the expression, age is greater than or equal to 18. So we're checking this person's age, and our voting laws here, you have to be 18 or over to vote. So we're looking to see if our age is greater than or equal to 18. If this resolves to be true, or a non-zero value, and the way this works, the value would be 18, the result of this. So that's non-zero, that's true. We'll come here and we'll do this part. This part of the expression, this value, true, we've already set it way up in our program someplace to be whatever we consider to be true, and that's generally going to be 1, non-zero. This will be assigned into here. So this value, true, however it's defined earlier in our program, will be put into the variable vote as its value. So you can see that if age is greater than or equal to 18, true will be put into vote. If age is not greater than or equal to 18, then the value of false, whatever we have done with a pound define. See, these are in all uppercase. Remember, when we define constants, we generally make them uppercase, so you can see this. It's not another variable. So true or false, probably 1 or 0 if we define it properly, will be assigned over here into vote. And that's a conditional expression. It's the question mark and the colon, and we have a test, a true result, and a false result that makes up the whole part of a conditional expression. These can get very complicated, but they can be quite elegant if you learn how to code them properly. They just kind of come to you when you're starting to really get into some coding and you have a condition like this, and it dawns on you that, well, this would be a perfect place for a conditional expression. You need the question mark and the colon, and we know how it works now, so now we're going to watch for places where we can use the conditional expression. Let's take a look at something called precedence and order of operation. Precedence and order of operation is important, but I don't want you to be scared off by it right now. I'm going to show you a table here on the next slide that it looks awfully complicated, but in some ways it's just common sense. If you don't understand precedence and order of operation, then you can get into issues where there are problems occurring, but you don't know why. Maybe mathematical outputs are different than you really believe they should be, or that you've even calculated by hand. But again, you don't know why they're off. Precedence and order of operation can do that to you. For example, let's take a look at this. Here we have an array called A, and it's going to have a bunch of elements in it. Like, let's imagine that this sentence is an array, which if this was a string in the C language, it would be. So here's the first element, which would be A sub 0, is this letter C. And then there's A sub 1, sub 2, sub 3, sub 4, as you go out across this string. And remember, hello world, that was a string. The H was at sub 0 at the very first element, and then there was another letter, and so on. That's the same thing we have here. So here's this little array called A, and some element here, I, this is a variable, and it could be 0 through whatever this number would be out through here. If we want to take that value and increase it by 1, this number in here, this index, we are saying that A sub I is equal to that value incremented. So we're saying that whatever is in a particular location that is referenced by I, 0, 1, 2, 3, whatever I is going to be equal to that value of I incremented. Well, here's where precedence and order of operation gets us. Which I are we going to use in here? I before it is incremented, or I after it is incremented with the plus plus, the post increment operator? Well, this is not specified by the C programming language. It is up to your compiler and up to how your compiler works with your particular computer to decide on the best way to do this. Bottom line, don't do this. You would want to increment I someplace else or read the value of I out of this other variable or some other place in your program, then increment it, then use it as an array subscript. You would not want to form a statement like this because it is so arbitrary and it is leaving decision making up to your compiler, which you don't always want to do. Same issue down here. Here we're saying that the value of x is equal to the result of the function f. F is going to be called, and then some result will come back from the f function, added to the result of the g function. We're going to call this g function, and it's going to do something and give us a number back. So these two numbers will be added together and then put into there. If f and g both work on another variable, and that variable is affected incorrectly, if f is called first or g is called first, then we're going to have a problem because we can't tell the compiler which one of these to do first. It will not necessarily do this function call and then this function call. It might decide to call g first and execute the statement this way. We can't tell the compiler which one of these two expressions to do before the addition. And then, of course, that will all happen, and then the result will be assigned into x. That we understand. So if you're going to do something like that, you need to make sure that f and g don't bother the same variable between them, that they don't cross paths, because we cannot determine which one of them is going to win this foot race. That is precedence and order of operation. Now let's take a look at this next table here. And this is in the K&R book and many other C programming books that you'll find. This is the typical order of operation. So you can see that operators like the function, parens, array, subscripts, these we haven't talked about yet. They're going to deal with structures and pointers and things like that. We'll get to them in future chapters. And here we have several other operators that we've already looked at. This one we haven't looked at yet either. That's a little different animal right there. Then the type and size of operators. We've looked at type when we talked about typecasting, but we haven't seen size of yet. So some of these are unknown to you, and that's okay. I promise we'll get there. And here's all the different, here's our bit shifts we looked at, and comparisons, less than, equal, and so on. And the order that they are associated, left to right, right to left, how you read them when you see them in a statement. And here's our unary operator for the binary and exclusive or. And here's our logical and logical or. This is the conditional expression we just looked at. Remember the question mark and the colon, and it's read right to left. And here's some of our assignments down here. And this one continues on. That's our bit shift right. And then the comma operator, we're going to see that very shortly. We haven't looked at that one yet, but it's pretty simple. So that's our order of operation and precedence table. Again, you won't really need it unless you get into some pretty complicated programming that is going to depend on the order of operation. And hopefully you won't be there right away, especially not in the as you begin learning the C programming language. But again, I do want you to be aware of it and that there can be issues so that you're not really scratching your head and then eventually pulling your hair out at 2 o'clock in the morning trying to fix something. So just be aware of this, and let's move on.